Looking at the voltage magnitudes, if we were to add those up, then we'd have 0.515 volts plus 3.641 times 10 to the minus fourth plus 0.485, and this is volts here, this is volts, and what we're going to find is that that's greater than the 0.707 volts, the RMS value, that I would normally think I should get, because we did RMS calculations here. The voltage was in RMS, our current is going to be in RMS, so we would think that if we could add these up, that it would come up to this value, but it's not. And the reason is because you have these phase angles in here. So if we wanted to verify Kirchhoff's voltage law, we can say the voltage of the resistor 1 plus the voltage of inductor 1 plus the voltage of capacitor 1 is equal to V1, the source, if we add them with the phase angles. And I'll leave that exercise up to you to determine, but it does work out. If you take the phase angles into account, convert these voltages to their rectangular equivalent, add up the reals, add up the imaginaries, and then convert it back into polar, you will come up with this value. So the whole part of doing an AC circuit is remembering that everything has to be done in phasors. Now there's an interesting value that we get by looking at the difference in the angle between the current and the voltage, and we call it the power factor. And that's equal to, for the series circuit, is equal to cosine of theta V minus theta I. And that's also equal to the resistance divided by the impedance. And it's the magnitude of the impedance. And it turns out in this circuit that power factor is 0.728. This power factor is an indicator of just how well the peaks of the current and the voltage line up. If the power factor was 1, then the peaks would line up. So a power factor of equal to 1 means the peaks are lined. A power factor of 0 indicates that the peaks are opposite each other. Now, why are we interested in power factor? Well, because the current and voltage at the power supply, at the source, are not in phase, we have to adjust our formula for the power, the total power. And remember that only the resistances will dissipate power. The inductor and the capacitor store energy, so they do not dissipate. So in this case, I have to do the magnitude of V1 times the magnitude of my current. This is getting rid of the angles and just giving me the total length, times my power factor. And when I calculate that for this circuit, I get 2.65 times, let me redraw this, 2.65 times 10 to the minus fourth watts. Now, since the only power dissipated, this was the power supplied. If the only power dissipated is in the resistance, then this formula, the magnitude of the current squared times the resistance, should equal the same. And it turns out that it does. 2.65 times 10 to the minus fourth watts. Now this power factor is for the series circuit. There are other forms for the other circuits, parallel and the more complex. The parallel is usually easier to figure out. The more complex circuits, the power factor is a little more difficult. But this power factor is very important if I want to take a look at the power supplied and have an actual value that meets up with the power dissipated.